This video is supported by the National Science Foundation.
Hello, I'm Olivia and I am a member of the Florida Institute for National Security at the University of Florida. I'm here to finish up our tutorial on reverse engineering integrated circuits from scanning electron microscope images using artificial intelligence for hardware assurance. This video is part 4 of this module, so if you have not already seen the first 3, you should probably go do that. You can find links to the first 3 videos in the description. Our objective is still the same. Follow along with the tutorial and complete a project on hardware reverse engineering using artificial intelligence. You can use this project as a resume builder for your next job or to support your current one. Last time, we went over several topics in unsupervised machine learning and applied them to our project. Specifically, we extracted some features, used k-means clustering for segmentation, and looked at cluster centers to gain human understandable insights. In this lecture, we will be introducing some topics in supervised machine learning and applying them to our code pipeline for the project. Again, this video assumes you have already watched the first 3 parts, so if you did not, please refer to the prerequisites in the description. As always, this tutorial is best if you follow along with me, so pause, rewind, or slow down this video when needed and refer to the documentation. Quick recap from last time. While unsupervised learning models learn without ground truth, supervised learning models learn from ground truth. So in our case, the ground truth images. Kinda like when you're studying for an exam, unsupervised learning is when you're given practice problems but no solutions to study from and are just told to figure it out. While supervised learning is when you're given practice problems with solutions that you can just directly study from. In the context of the machine learning segmentation pipeline introduced last time, we will be focusing on 2 stages this time: evaluation and segmentation. When discussing about machine learning, we need to understand the difference between training and testing data. Training data, as its name implies, is used to train or teach our machine learning algorithms. Testing data is used to test or evaluate our algorithms. To make sure our algorithm can generalize well to unseen scenarios, we need to ensure the training data and the testing data are separate. We can do this by adding a train-test split, which is typically represented as a ratio. For example, an 80-20 train-test split means 80% of the data is used for training, while the remaining 20% is used for testing. If we don't have a train-test split, we run into what's called the overfitting problem or the memorization issue. Basically, if there's no separation of the training versus testing data, there's no guarantee our model is actually learning anything meaningful. It could just be memorizing. In the real world, this is equivalent to, say, a math teacher just giving students a copy of the final exam with solutions. Sure, the students will probably get an A in the class, but do they really know what they're doing? Would you trust these students to become engineers, doctors, or scientists? Probably not. This is why model generalization and the train-test split is so important. To ensure our model generalizes well, training data must have the following traits. It needs to be representative, so in the context of the math exam mentioned before, this means that the students or the machine learning models need access to a math book instead of, let's say, an art book to prepare. Training data also needs to be correct. Students can typically learn from a math book even if there's a couple of typos, but if the majority of their study material is wrong, it'll be difficult for them to do well on the final exam. Finally, training data needs to be sufficient in amount. 1 or 2 examples may not be enough for some students to grasp a math concept, so having lots of examples is better. Now that we've learned a little bit about the importance of generalization and having a train-test split, let's apply this to our project. If you've been following along with me, you should have a project set up similar to this, where lecture 3 is from the previous lecture. Let's duplicate this and rename it. And I'm going to name it 4A because we have a couple different files we're going to be creating in this lecture today. Open it up. Make sure it runs. So restart and run all. Everything's looking good. So for the train test split, we want to actually move up where we read in our ground truth to the very beginning. So I'm actually going to cut this and move it all the way up to the beginning. Down here. So hit run. Ground truth is up here. And now when we get to the train test split, we want it to be in between where we extract the features and when we actually use the features. So let's go ahead and insert a cell above. Let's name it train test split so we remember what we're doing. So for this, we're going to need to import sklearn dot model selection. And then we want to do an 80-20 train test split. So the test percent is going to be 0.20. The number of test rows, or the number of rows that will be used for testing, is going to be the integer of the test percent times 800, because our image is 800 by 800. The number of train rows is going to be equal to 800 minus the number of test rows. So I'm just going to copy and paste this. And let's just double check, make sure it's printing off okay. So the number of test rows and the number of train rows. Let's hit run. It moved me. 160, 640. That's about what we want. So let's actually do the train test split now. So we are going to do feats train. So the features used for training, the features used for testing, the ground truth used for training, and the ground truth used for testing equal to, let's move this up so you can see, sklearn dot model selection dot train tests split. It's long. Features, because this is what we named our features from last time. So features, ground truth dot flatten, because it's looking for one-dimensional ground truth, whereas right now it's an image. As type, and it's currently a boolean. We need an integer, so we have zeros and ones. And the test size is going to be equal your tests percent and shuffle. Let's set shuffle to false so we can still interpret what we're doing. So hopefully this runs, and we can figure out if this runs by printing it off. Let's figure out the shape. So the training feature shape looks about right. Cool. So now we want to actually use the training and testing features. So let's take a look and see importing sklearn, number of clusters, random state. We don't want to use all the features. We only want to use the training features. So we will be using feats train. And the clustered image will be only on the training features. And then because it's now a weird shape, you got the number of your training rows by 800. And hopefully this runs. Perfect. And I believe the post-processing is still the same. Awesome. And we could just delete this cell actually because we're not using it. Delete this one cell. And then the evaluation. So this is now going to be the training evaluation. So I believe you need the ground, instead of ground truth, because right now segmentation is only the training segmentation information. So you need GT train. IU is 0.88. And then to visualize the results, I believe we have to double check. The original image, it's only going to be the first couple of rows. So 0 to n train rows, 0 to 800. And I think that'll run. Perfect. And then we've got the model interpretation. Okay. So now we've got the training steps. I'm actually going to combine everything into one big block because it's kind of hard to have everything split up. So let's do that now. So I'm actually going to name this the training block. And then move content from post-processing can go up. Everything from the evaluation and the visualized results can also go up. This is just making things easier for us later on. These are empty, so I'm just going to delete them. So delete these cells, delete cells, delete cells. Okay. So I should be able to just restart and run all through the kernel. Just to double check, make sure that I didn't lose anything. So we've got our cluster image using only the training data, so it doesn't go all the way down to 800. We got segmented, you got the result overlay. Awesome. So looks like performance-wise, the IOU for the training data is 0.88. Now let's see how it does on the testing data. So ideally, the testing data, the performance will not decrease very much. So let's grab this, copy everything, go down, and then name this testing. And just to double check, make sure I didn't miss anything. So we're testing, we're not training anymore. So we already have our model, so we can't fit anymore. So remove this. You've got our cluster image, feats train. We want to change this to feats test. The clustered image now needs to be reshaped, so this is going to be the number of test rows to 800. That should show the clustered image. I believe post-processing doesn't change anything, so that should be good. And then for the IOU, it'll be ground truth test. And then in visualizing the result, it's going to be the number of train rows to the end. So that should give us everything. Hopefully this runs. We'll find out soon. Awesome. So this is now the testing data. The performance is actually slightly higher. So that's really good. Ideally, we want to make sure that our training score and our testing score are as close as possible. So 0.88 to 0.89 means that it's generalizing pretty well. Decision tree classification is a supervised machine learning technique that can be used for image segmentation. It operates by using simple decision rules, such as greater than or less than, in a hierarchical fashion in order to classify data. Since this is a supervised technique, it requires training data, or the training features, as well as the training labels from the ground truth. To illustrate its operation, we have prepared the following example. Suppose we extracted two features, feature 1 and feature 2. They could represent intensity and edges, for example, and we plot each pixel based on these two features. Now, unlike before, there really is no clean line that you can draw that separates class 1 and class 2 pixels. So we do the best we can with what we've got. We've noticed that all pixels with feature 1 value less than 0.4 are in class 1, so we use that rule to start building our tree. So this reads, if feature 1 is less than 0.4, if this statement is true, then it belongs in class 1. So in our diagram, we will use left for true and right for false. Next, for pixels with feature values 1 that are greater than or equal to 0.4, we can subdivide, where feature 2 is at 0.6. So we can use the second rule to extend our tree accordingly. So this reads, if feature 1 less than 0.4 is false, so in other words, if feature 1 is greater than or equal to 0.4, go right. And now, additionally, if feature 2 is less than 0.6 is true, it's in class 2. Otherwise, it's in class 1. Now, this was a super simple example, but it illustrates the main concepts. If you're interested in learning more, please refer to Lowe's article entitled Classification and Regression Trees referenced in the description. Now that we've gone through decision trees, let's apply this to our project. Now that we have our train test split, let's go back and change up our methodology. So let's close out 4A, shut down, duplicate, and rename. And let's call it 4B. Open 4B. Go kernel, restart and run all, just to make sure everything is in working order and everything was duplicated properly. Awesome, the IOU is still 0.89, so looking good. We want to go up, and we want to change our methods from the unsupervised k-means to supervised decision tree. So for this, we are going to need to, from sklearn, import tree. So for this, the model is going to be sklearn.tree dot decision tree classifier. It does have a random state, but it does not need the number of clusters, so I'll take this out. I'm actually going to give it another parameter called impurity decrease equal to 0.01. This is completely optional. I'm only including it to make sure that my decision tree is a certain size because I'm running this live. You don't need this if you want to have it be a larger tree. So when fitting, this is a supervised machine learning technique, so in addition to the training features, it also needs the ground truth labels associated with them. So ground truth train. Hopefully this runs. Awesome. And the performance is IOU is 0.88115. So not really a huge change based on the k-means results. However, you'll notice that one of the benefits is that because this is directly using ground truth train, it's a little bit less volatile with the random state. So you can play around with the random state as much as you want, and it will pretty much usually think the foreground is the foreground, whereas k-means had no idea what was what, so it occasionally confused the background with the foreground. It was completely inverted. So that's one little bit of a benefit. Now let's see if we can visualize the model. So cluster centers don't apply here. So let's see. There's a couple different ways to visualize the results. You can use sklearn, .tree, .plottree, and this takes in the model, the feature names, and this needs a list of the feature names. I'm actually going to move this up in the beginning where the features are actually extracted, so I'll actually cut that up and go all the way up to where the features were. And then I'll paste it here. So feature names equals the list of the feature names. So these need to be strings, so add these in and run. The reason why I have it up here is because if you want to play around within these features, I just picked any 3 random ones, but you can pick whatever you want. It's a little bit easier to edit as you go. So now we've got feature names. Go back to where we were before. So feature names equals feature names. And then we got class names. So we've only got 2 classes, 0 and 1. That correspond to the background and the foreground respectively. So background, I'm just going to say BG for background. And foreground is FG for foreground. And then I'm going to add in a couple additional parameters just to make it look pretty. You don't need these, but it does make it look more visually attractive. Proportion equals true. Build equals true. And then I believe this is able to be plotted through matplotlib. So plot show. Hopefully this runs. Okay, so this particular tree is mainly focusing on one of the features, intensity, and it claims that anything with intensity less than 0.4 is background, otherwise it's foreground. So this is a really small tree because I restricted the size with the minimum impurity decrease parameter earlier on, but you can certainly take that out if you want a larger tree, see if there are some other features that could be used. That's one way to visualize your tree. Another way is you can just print it off in text form. So there's sklearn .tree .export text. Text, I can spell. Model, and it does accept feature names equals feature names. So hit run. This is just saying the same thing that's up here, except a lot more simply. This one's agreeing that if the intensity is less than or equal to 0.41, it's class 0 or the background. Otherwise, it's class 1 or the foreground. So if you don't have a lot of features, it can look pretty good like this. If you have a lot of features, this can take a long time to print off, so I will occasionally use the text version. And then testing, we can take this out because it's no longer k-means. Just want to run, make sure it generalizes okay. And now, yep, about 0.88. So that's pretty similar to the training IOU score, so it's generalizing decently well. Random forest classification is another supervised machine learning technique that can be used for image segmentation. Random forest is considered a meta-estimator that uses an ensemble or group of decision trees in order to achieve better generalization when classifying data. Each tree is trained on a random subset of the data, and classification is made by averaging the individual tree results. You can think of it as collective wisdom. Get a bunch of trees and hope that the group or the forest is smarter than each individual tree. Since this is a supervised technique, it requires training data, or the training features, as well as the ground truth, as well as the number of estimators, or the number of trees in the forest. To illustrate its operation, we have prepared the following example. Suppose we have the following 3 decision trees, similar to the one discussed in the decision tree classifier example. We've only got 2 features, feature 1 and feature 2, so for example, intensity and edges, and pixels are classified based on these 2 features. Now suppose we have a test data point with a feature 1 value of 0.55 and a feature 2 value of 0.55. Navigating through tree 1, we realize that the test point's feature 1 is not less than 0.4, so this statement is false. We navigate right. Now we compare the feature 2 value of the test point, so 0.55, to 0.6 and find that the statement is true. So we go left. So we have that tree 1 thinks that the test point is in class 2, or blue. Navigating through the second tree, we look to see if the first statement is true. So if feature 2 is greater than 0.5, so 0.55 greater than 0.5 is true, so we go left. So we land on class 1, or orange. So tree 2 thinks we're looking at class 1. Then we navigate through tree 3 and realize that feature 2 less than 0.5 is false, so we navigate right, and then we end up with class 1. So tree 3 also thinks that the test point is in class 1. So going by majority rule, we've got 1 vote for blue, 2 votes for orange, so the final output of the forest is orange. Again, this is a super simple example, but it illustrates the main concepts. If you are interested in learning more, please refer to Breeman's article entitled Random Forest, referenced in the description. Now that we have gone through random forest, let's apply this to our project. Now that we have trained our decision tree classifier, let's take a look at extending it to random forest. So right now I have lecture 4B, gonna close that out, shut it down, duplicate, and rename. And I'll rename it to 4C. Open that up. Kernel, restart and run all, just to make sure everything's in working order. Good. IOU is still 0.88. Now let's go change the method. So go back up to the training block. And instead of tree, you're going to take ensemble. So instead of this, you will take sklearn.ensemble.random forest classifier. It needs the number of estimators, so num, or the number of trees in the forest. I'm going to set it to a really low value because I'm coding live, but I think the default is 100. I'm also going to keep my min impurity decrease. Up to you if you want to keep this, but I am including this in here so that way I can restrict the size of my trees and it runs real time. So let's run. Hopefully that actually made it small enough to run real time. Awesome, so it ran. IOU 0.88. So looking pretty good. The model interpretation is going to be a little bit different here. So we're actually going to take this and delete it. And then we need to see the for I in range, length, feature names. Print off 2 things. Feature names index at I, so we get the name of the feature, separated by a dash, And then we want to get the model dot feature importances. And I think there's an underscore randomly at the end if I remember correctly. So we can run this. Hopefully it runs. So as we can see here, it's listing all the different feature names and how much the model thinks they are important in determining the foreground versus background. So this is telling me that it's using 75% intensity, 22% the corner data, and very little about the edge data. To make sure that this is robust, we want to run our testing block. So running testing block IOU is also 0.88. So again, similar as before with the training results. So that means properly generalizing well. The reason why we sometimes want to use random forest over decision trees is the concept of sometimes each individual tree has some intelligence, but if you have a group of several slightly intelligent models, you might have a nice group intelligence. There are a number of extensions that could improve your project. For evaluation, we used a simple train test split. For a more robust evaluation, you can use k-fold cross-validation. For segmentation, we use decision trees and random forest. You can always play around with some of the parameters of the methods we used, or use other classifiers such as nearest neighbors, support vector machines, or naive Bayes. There are also other ensemble methods you can use such as add a boost and gradient boost. The explainability methods may differ for different algorithms, so you may need to search if you're going to use a different method. As always, we encourage you to experiment, see the effects for yourself, and try out some methods that are maybe not listed on this slide. For some inspiration, please refer to the sklearn library documentation linked in the description. In summary, this is what we covered today. We recapped unsupervised versus supervised learning and focused on supervised learning this time. We discussed the importance of model generalization and incorporated a train test split into our pipeline. We applied decision tree classification as a supervised learning segmentation technique and visualized our trained model. We also introduced the concept of ensemble methods and used the random forest algorithm to try to achieve better generalization than just one tree. And we also suggested a few potential extensions for you to look into and experiment. That concludes the end of this module. We look forward to seeing you in future videos where we will be focusing on deep learning. Until next time, thank you for watching.